So, of course, I'd like to start by saying thank you, everyone, for joining. My name is Cody Armstrong, and today we're discussing advanced assembly motion in Onshape. So, we're going to focus on a few of the questions that have been asked around some of the more advanced movements that you can get at the assembly level in Onshape. So, that's really going to be the focus. We're going to focus a lot on relations today and some of the more advanced, mechanisms, let's call them, and how to create those movements in Onshape. So that's really going to be the goal. We're going to start things pretty simple with a simple explanation of mates and relations, but then we're going to get right into examples. We're going to start with examples of gears and screw relations and all those types of things, and then get into some more complex hypothetical examples. How would you handle a cam? How would you handle a part following a path? Those types of scenarios, and how would you design in that scenario? How would you create the relations or mates that you need in those scenarios? As I always say in these webinars, I really encourage you to ask any questions that you like. There's a questions section there in the GoToWebinar control panel. Feel free to ask any question that you'd like, and I'll do my best to stop and answer the questions as we go through things. One thing I do want to stress is I'm not going to spend a ton of time on the basics of mates. So if this is your first exposure to assemblies in Onshape, it may be best to check out one of our, introducing Onshape assemblies or Onshape mate webinars that we've done in the past that goes over the more basics of creating simple mates. We're really going to focus more on some of the more complex mates and where they're used, and then also a lot today on relations, as I discussed. So just a quick prerequisite. If this is your first exposure to assemblies, definitely check out the past webinars we've done on the basics of mates. All right, so let's dig into it. Now, I want to start with a very short intro into the differences between a mate and a relation. And those are important as we start to discuss mechanisms and moving parts and interactions between moving parts. So, what is a mate? Let's start with the basics. And it's a way to constrain a part at the assembly level or constrain an assembly at the assembly level relative to each other, right? So when you begin to insert parts and mate parts relative to each other, you're constraining them relative to each other. And that process is often referred to as a mate. It's not unique to Onshape, of course. It's been around for a very long time in a number of different CAD systems. What is a little bit different is how we create the mates. We use a mate connector to define the relationship. And I know there are a lot of older CAD systems out there that don't use mate connection points. They use faces or combinations of faces to define a part's relationship. So that is a bit different than say a SolidWorks, for instance. So we use mate connectors to define the relationship between parts, and we take two mate connectors, one from each part, and we bring those two mate connectors together, and the mate that you choose defines the degrees of freedom that that part has, right? So, for instance, a revolute mate has a rotational degree of freedom. It's allowed to rotate. So the mate that you choose is what determines how much movement there is in that, between those two parts that you're choosing for your mate. So that's kind of the basics of a mate in Onshape. And the reason I bring this up in this webinar is it's important to understand, the difference between this and a relation. A relation in Onshape uses or creates a relationship between mates, right? Think of parts that interact with one another. An arbor press or a machine vise are two good examples of that, where you have, a base part and a part that moves up and down relative to it. You have this interaction between parts. And the way a relation works in Onshape is it uses existing mates that you've already created, to define relationships between parts. And essentially what you're doing is you're defining a relationship between the mates that were already existing. Right, now, I'll go over this in greater detail in just a bit, so bear with me if this is still a little confusing. The important thing to remember here is the degrees of freedom, the movement that the part has, is still always defined in the mate. All we're really doing in the relation is defining a relationship between the parts. So, for every rotation of this moves X. That's a relationship between the mates, or between the two parts. But the movement of the part, how it moves, the rack pinion, you have the up-down motion, that linear motion is still defined in the mate, right, in the case of the slider mate. So you have four different relations to choose from: gear, screw, rack and pinion, and linear. So those will give you the various ways of interacting with your assembly and creating realistic motion when there's interaction between parts, like in these examples. So that's a simple thing to understand. Again, you have the concept of mates. Those are always used to position your parts, to get the correct movement, the correct degrees of freedom. And then we have relations, which allow you to tie parts together with the relationships, right? To make one interact based on the movement of another, to put it simply. So let's dig into it. Now, what I'd like to do here is kind of treat this as an FAQ, because I think that's the most interactive way to accomplish this. And what we've done what we've had over the last few years is a lot of webinars where we get tons and tons of questions about different types of motion. And I'd like to go through and just highlight a few of the ways that we create some of the more common motion types that you may be used to. I want to start with a simple gear relation. So the question, can you animate gears at the assembly level? And the answer is yes, you're using a gear relation. And what we do with a gear relation is we define the ratio between two gears, right? More importantly, we define the ratio between two rotational degrees of freedom, right? So the important first step for any gear relation is mating the gears into place, right? And having that necessary revolute or cylindrical mate in place that allows for rotation, right? In Onshape, we take the gear relation, we define the relationship between the two mates by choosing, which ones in order and the ratio. So it's very simple. Let's jump into a quick, simple example of this between two simple gears, right? And what we do is we create a gear relation, and we define the two mates that define our rotational degrees of freedom for the gear. So again, all of these relations that we're going to show you, the gear relation, the rack pinion, the screw relation, they all have a prerequisite of mates. You must have the parts in place and mated accordingly. Now, a gear relation means the gear needs to be able to spin, right? It's a simple thing, but it's important to stress. These are mated with revolute mates, meaning they're free to spin. They're just not related to one another. If I grab and drag, you can see if I turn one, the other doesn't move, which is what I would expect. So we have our two revolute mates allowing the gears to rotate. They're correctly mated into place. We just need to establish the relationship between the two. Therefore, relation, right? So I select gear relation, and I define the two mates that attach the parts, in this case, to their simple base, right? So revolute 1 and 2. And then just define a ratio, right? So we can say 1.25, and that's 1.25 ratios of rotation of this for every one rotation of that. Right, so you're establishing that ratio. Now, how you determine that ratio is up to you, if it's pitch circle diameters or number of teeth, but this is what you're entering in as the rotation ratio of one next to the other. Right. Now, one important tip that I have is you always want to test your motion out. And there are a few ways to do this. I can grab and drag as I'm doing here. You can see now I am getting that correct rotation ratio. When I grab one, the other moves at the correct ratio, so the teeth mesh properly. Of course, I can animate, right? So I can right-click and mate in the assembly, choose animate, hit play, and it's going to animate the motion, right? So you have a couple different ways of verifying that it's correct. And the reason I stress verifying that it's correct is there may be a scenario where the direction is reversed. Right? So what you'll end up with is essentially the opposite of what you're expecting. And this is the case for any of the relations that we're going to discuss, so just keep that in mind. But you'll want to verify that movement by grabbing and dragging, animating, whatever way that you prefer to verify, just to make sure that everything's moving in the correct direction. Right? That's an important thing to stress. Now, this is a kind of an aside, but it is specific to gears, and I do want to mention it. I have been asked the question quite a few times, how do you get the gears to mesh properly? And there's no way to tell the faces, come in contact or anything like that, but what you can do very easily is just edit a mate connector and rotate it accordingly. right? So I can go into any one of these mate connectors to locate either gear, edit the mate connector, and do something like rotate. Now, it is somewhat of a trial and error process unless you know the exact angle of rotation that you need. You could do some quick math to figure that out. But again, this is where you would punch in that value. And that will allow you to rotate one gear relative to another, aligning those teeth. Because the reason I mention this is if you're getting these gears from external sources, or if you're modeling them in different tabs or different documents, they're unlikely to come in perfectly aligned. Chances are you'll need to rotate one or the other to get the teeth to align correctly, right? So that's just kind of an aside. It's a gear-specific tip that I have for you, but you can right-click, edit a mate connector, rotate about the Z until the angle lines up and the teeth line up. Right? So that's a simple example of a gear relation. Again, we use existing mates. In this case, we have a mate for each of the gears that attaches it to the base plate, and we use each one of those to define a ratio between them. Now, you can take this to an extreme, right? So you could go to a full-blown, planetary gear set where you have many, many gears tied together in relation, creating a, in this example, full-blown planetary gearbox. But each one of these is just an independent gear relation, right? So it's done no differently than what I just showed you. It's just the math of figuring out what the ratio should be, and then setting everything up, right? So another question that often comes up is, okay, you've shown a simple gear example. What about worm gears or helical gears or any of those types of scenarios? And the answer is the same. It's still the gear relation. All we're really doing is defining a ratio between two rotational degrees of freedom, and those rotational degrees of freedom can be in line with one another. They could be opposed. That's up to you, right? And so another good example that I like to show is worm gears. Worm gear is another example where it is simply a gear relation, between two rotational degrees of freedom. It just so happens that, because of the nature of worm gears, the ratio is way different. But the process of creating a worm gear relation is no different than creating the last relation that I showed you, right? And the same goes for, just about any kind of gear relation that you could imagine. So take this as an example. Let's hide a few parts here. I'm just using the Y keyboard shortcut to hide, one of my personal favorites. And so we have this worm gear assembly, right? And what I want to do is define a ratio between them. And you can see I have a rotational degree of freedom for the worm gear, a rotational degree of freedom for the worm itself. And so I can drag them independently of one another, but I have no relationship that ties the movement of this one to the movement of the one below it, right? So there's another example where I just use a gear relation, define the two rotational degrees of freedom that I want, and then define my ratio, right? So for every one rotation of this, I want 30 rotations of this, right? Hit the green check, and let's do a quick animate. Right-click, animate. I'll hit play. And there is our worm gear animation, right? Pretty slow, but you get the idea there. For every one rotation here, you end up with 30 rotations here, right? So again, any kind of gear scenario, just about this is going to be the relation that you choose. And you're really just defining, the two rotational degrees of freedom. In this case, revolute 1 for the worm gear and revolute 1 for the worm, and defining a ratio between the two, right? And that ties them together in that relation, right? So that is the gear relation, an important one to stress because it's useful in a number of different scenarios: worm gears, helical gears, normal, gears like the example I was showing you just a moment ago, even all the way out to, planetary gear sets and so on. It's all using that same gear relation. All right, moving on to the next movement that we get asked quite often is rack pinion motion. And we do have a dedicated rack pinion relation. So it allows you to define a ratio between your rack and your pinion for amount of linear travel. Essentially, for every one rotation of X, you get X amount of linear travel, and you define what those 2 degrees of freedom are. So this is a bit different than the gear. In the last example in the gear, it was 2 rotational degrees of freedom, right, for the 2 gears. But in this example, we have 1 linear degree of freedom and 1 rotational degree of freedom, right? So a bit different in the sense that the mates that we choose, the degrees of freedom that we choose, may be different. So let's jump into a quick example of this. Now, again, the key here is first defining the type of motion that should be allowed, right? So I should have this up-down motion. I should have this rotational motion before I add any kind of relations. And you can see the slider mate and the revolute mate that define those 2 rotational degrees of freedom. What we really want here is now a relation so that when I move one, the other moves accordingly, right? So when I rotate this, I would expect to get a certain amount of travel on that, right? And so we define our rack pinion relation. We define the 2 mates, 2 degrees of freedom, a linear degree of freedom, and a rotational degree of freedom, right? And then we define what is our distance per revolution. So how far should this move for every 1 rotation of this revolute? So it should be, let's say, 2.25, right? Now I'm going to hit the green check OK. And now there's a relationship between the 2. I can do the simple grab and drag and see it's going the wrong way. Or I could right-click, animate, play, right, and see it's going the wrong way. Another good example of a reason that you'll want to double check that. Now I need to go back into the relation. Let's edit and check reverse direction, right? And now when I animate, hit play, we get that realistic motion. All right, so that's a simple example of a rack-pinion relation. The key there being you have your 1 linear degree of freedom, you have 1 rotational degree of freedom, and you're tying the 2 together with a ratio, that relation. In this case, 2.25. And again, what you're specifying here is move this far for every 1 rotation of whatever mate that I've defined. In this case, the cylindrical mate associated with the handle here. So that's a simple example of the rack-pinion relation. Now, one thing I want to mention just briefly here is in all of these examples, I've chosen 1 mate and 1 mate. But just realize that's going to be the most common scenario, but you can use other things. One good example of this would be like a screw relation, where I may have both degrees of freedom in 1 single mate. That is acceptable. Maybe I have a revolute or a cylindrical mate, and I only need 1 rotational degree of freedom. You can choose which degree of freedom you want to control with your relation. So again, just keep in mind, I'm showing you 1 mate, but that's not necessarily a rule. You can select a lot of different things when you're defining relations. And I'll show you an example of this that kind of better highlights it in just a second. But that's a simple rack-pinion motion. Let's move on to the next example. And this next one comes in a lot of different forms. The common term I hear is linear actuation, thread movement. There's lots of different terms for it. But basically, you want to be able to rotate a part and move X amount parallel with that direction. So a good example of this would be a machine vise. Right, machine vise, you twist the handle, you expect it to go in or out. Right, linear actuation based on that thread on the spindle of the vise. So this is a screw relation in Onshape. Any kind of linear actuation, like the machine vise example, is a screw relation. And the key thing I would stress is you need 2 things. You need a rotational degree of freedom and you need a linear degree of freedom, right? And you're defining a ratio. So the amount of linear travel per rotation, very similar to the rack pinion mate in that sense that, for every rotation of the handle in our machine vise example, how far do you expect it to move in or out? And so that's the relation that you're specifying. So between this rotational degree of freedom and this linear degree of freedom, how much travel are you expecting, right? Now, you'll notice I mentioned the bottom note there, choose a mate or mates with a rotational degree of freedom and a linear degree of freedom. Now, in the last examples, I've shown you two different mates. In every example, there were two different mates associated with two different parts. But this may be a scenario where it's only one mate. And let me give you an example of where this is applicable. This is that same machine vise example, and you can see I can grab and drag, and it doesn't twist. If I twist the handle, I'm not getting that realistic, screw-like motion. When I grab the handle and drag it, it should move in or out. And if I grab the jaw, it should rotate as I move it in or out. All right, so realistic behavior. Now, the screw relation, you'll find it right here on the toolbar. It's very simple to use. Right? You select a rotational and a linear degree of freedom. Now, in the last two examples, that was two different mates from two different parts. But in this example, you can see there's a cylindrical mate, the very first mate in the list, that attaches this shaft to the actual vise base. Right? And that cylindrical mate allows the shaft to rotate, and it allows it to move in and out on the vise base. That's both rotational degrees of freedom that we need. That's all the motion that we need, and it's all in one mate. So in this example, I'm not going to select multiple mates from multiple parts. It's going to be one single mate that mated the shaft to the vise base. Right? Then, as I mentioned before, all you have to do here is choose what's your distance per revolution. Right? So in this case, we can say, actually shouldn't be, that's way too much, 0.5. Right? So for every one rotation of our cylindrical mate, right, we're going to move in or out 0.5. Right? I can hit the green check. Now if I grab the vise jaw, it moves accordingly, right? Although it looks like it would be backwards, at least for a right-hand thread. So let's go ahead and edit. Let's reverse direction and try that again. Yeah, that's more what I was expecting. Okay. All right. So again, the idea here is we are defining a relationship between degrees of freedom. In this example, the screw relation, we were able to use just one mate because that one mate had both degrees of freedom that we needed, and it perfectly defined a relationship. I think, the shaft and the vise base is kind of the quintessential example of that, where you have one mate that attached to part, and it also defines how it should relate to other parts. And then you just define, well, what's the ratio? Right? What's the distance per revolution? And I mentioned this just briefly, in other scenarios, but it doesn't matter whether you grab the end, you grab the vise base. It should act realistically in all of those scenarios. I get asked that quite often. It shouldn't matter. You should be able to grab it just as you would in real life on any piece of it and drag it, and it should all move, accordingly. So that is a screw relation. Any kind of linear actuation, that's the example that I kind of give you, but that's what I would use. Now, the linear actuation, right, needs to be normal to the actual rotational degree of freedom. And that's one thing that's different, say, from the last command that I showed you, the rack pinion relation. So in the rack pinion relation, it moved tangent with it, where in this case it's normal to it. And that is the difference, you would say, between something like a rack pinion and something like a screw relation. So that is the screw relation. Let's move on. All right, so the next one in my list, the next question that gets asked quite often is, what about cams, or linear movement via cam actuation? And the short answer is tangent mate. In Onshape, we have the tangent mate command that allows you to accomplish this. Essentially, it allows you to make faces or edges or vertices tangent to one another, and it will maintain that tangent relationship even as you move parts around. So the excellent example would be a cam and a follower, where I select all the faces of the cam as part of the command, right? I select the follower, and as I rotate the cam, it will maintain tangent relationship to the face of the cam, all faces of the cam, even if there's multiple. Now, what's really different about a tangent mate versus every other mate in Onshape is it does not require a mate connector. This is the only mate where you select faces. You can select faces. So you can also select edges and vertices, but faces are probably the most common selection, and it is different in that sense. In every other mate in Onshape, we select mate connectors and define the relationship between those. In this scenario, we are selecting faces, most of the time, right? And that is different. So I have a few different examples of this. It's a very, very simple command to show. So we're going to show a few different examples of it. All you need to do is select a face or edge and a face or edge. Two different selections here, right? And it will create that tangent mate between them. So let's go ahead and delete and start over with a new tangent mate. Now, tangent mate is kind of in its own category here in the assembly toolbar, and that's because it is, of course, a bit different. And then I'd select either an edge or a face, right? So if I select this edge, for instance, of the cam, right, and I select this face of the follower, it will ensure that those two remain in contact the entire time, right? So if I move this, you can see they remain together, right? Simple example, I know, but I wanted to start simple. If we do a basic animation here, you'll see it can rotate that full amount of travel and still remain in contact, throughout. So again, you can use faces. It will automatically do any kind of selecting of tangency. So you don't have to select all the faces of your cam. It should automatically do that for you. Or you could select an edge and the same thing. It will go through and select all the tangent connected edges. So you don't have to go through and select a whole bunch of individual faces of a cam. It should do that for you. You just need to select something from each part that you want to maintain a tangent relationship with, right? So that's a simple example of a tangent mate. I want to give you another example. Bear with me. The cylinder head. So this is really no different than the last example, just a lot more of them. So you'll see I have several tangent mates here and several slider relationships for each of the valves moving up and down in this example. So of course here you get the same end result, just with a lot more valves in place, right? So that is a simple example of cam actuation. And again, the key to it is using the tangent mate in the toolbar. Now, tangent mate has the name tangent mate for a reason. It works great in cams, but it also works great in other scenarios. The other scenario that I think is common, the question that I get asked often, is what about following a path? What if I wanted a part to follow a path that isn't necessarily linear or circular, just some given path that I specify? That's another example where tangent mate is really, really useful. The reason is you can tell a part to stay tangent with another part, and it will maintain that tangent relationship even as you follow a path, so to speak. So it's the same exact steps as what I just showed you, but the selections may be a bit different, right? So it's the same exact selecting a face on each part or edge, whatever you choose. But of course, the geometry, the reference, the examples that you have are going to be a bit different. Again, tangent mate does not require mate connectors. That's one of the biggest things I would stress. It is quite a bit different in that sense. So I'd like to start with a simple example of a part following a path. Let's say that I had a simple example of a pin following this groove that I've set up. That's an example where I would use a tangent mate. So all I do is I select tangent mate, and I select a face on one part and a face on another part. What will happen, as I mentioned before, is it will automatically select all tangent connected faces to whatever you select in these selections. So you can see I selected one face of this groove, but it automatically went out and found all of the tangent connected faces and selected them as well. So I don't have to worry about that as a separate step. I don't have to select each face of my path, in other words. Now, you can see the pin is mated, but it's in the opposite or reverse direction. So I'm going to go to the primary and flip primary axis, right? And then if I hit the green check and grab and drag this, you will see that it stays tangent to those faces as I move it along my path, right? It will stop as soon as it hits that corner because that is the end of the tangent connection. So it will maintain that tangent relationship between the faces as I move the part along the path. This is, not something you would use if it's perfectly linear, perfectly circular. There's probably something better in that scenario, like a revolute with a limit. But in the scenario where you have this kind of, organic path that you want to follow, tangent mate could likely be a solution for you. So that's all it really is. You're selecting, face or an edge or vertice and saying follow this path. All right. So those are some examples of the tangent mate. Another example I like to show is this fishing reel. So bear with me for a moment while I hide a few parts here. And if we take a look at how this fishing reel works, let's go ahead and animate with some of these parts not showing here. And let's hit play. So we have some gear relations here, but one thing I want to stress is the up-down movement of the spool in the fishing reel. And if you look closely, it's because of this part here located in the gear. So just real quickly here, let's hide this part, the oscillating slider. Right? What you'll notice is a groove cut into the path here and a notch on one side of the gear. And you'll see it lines up with a corresponding groove in this slider. And so what happens is you get that up and down motion from a tangent relation between the actual pin and in the gear and the slot in the slider. That's what gives that spool the up and down motion. It's just a tangent mate that follows that path cut into this slider. Right? And that slider has the amount of movement that you would expect, the up-down movement that you would expect to see when animating the spool. Right? So when reeling this in, so to speak, you would expect that up-down movement, and you get that from the pin traveling up and down in this slot. Right? So just give you another example of where tangent mate makes a really big difference. And again, it's different in the sense that you're mating, in most cases, faces together, and that's different for Onshape, but it allows you to do a lot of different things. Cam actuation is a good example, but also this following a path of another to get kind of the certain movement that you're looking for. Right? All right. So, questions. I tried tangent mate yesterday, a welding gun moving along a seam between two cylinders. I got the message invalid mate. Any clue as to what I was doing wrong? I tried tangent mate yesterday. Cylinders, I got the message invalid mates. I would look at what other mates are constraining those parts. Are there any other mates constraining those parts? It sounds like invalid mate means there's some kind of invalid mate condition with the tangent mate and something else. So I'm curious. The gut reaction to the question would be, what other mates? And if you suppress one of those mates and try it, do you get the same error? That might be something. I don't know if that's an issue or not. The follow-up to that, the weld gun and cylinders were not touching. Should they have been? They do need to touch, and that's a very good point. So the question was, in this example, he's using weld guns and a cylinder. Do they need to touch? And it is, yes. Tangent mates the faces need to touch in those examples. If they don't, there may be other ways you can kind of mock that up, but using something else like edges or vertice. But if you're selecting faces, they need to touch. So the pin in the slot example where I was going through that slot, that pin fit perfectly in that slot. And the same goes for this fishing reel example. The boss perfectly fits in the pin so that the faces touch. Right? That is, yes, a prerequisite. All right, so moving on. So that is the example of following a path. I have one final example that I wanted to show you, and it's a very commonly asked question. How do I get realistic swivel motion in Onshape, where it's free to rotate in all directions, free to pivot in just about any direction, but can't move in any linear direction? right? It can't, move left, right, up, or down. It's only allowed to pivot, only allowed to rotate in all directions. And the short answer to this is the ball mate. The ball mate in Onshape allows you to rotate in all directions, but doesn't allow any linear movement up, down, left, or right, X, Y, or Z. Right, so perfect for the swivel on the eye scenario, the spindle. If you think of kind of the classic independent suspension with this swing arms and a spindle, the spindle would need to be free to pivot up and down and left and right. And so that's an excellent example of the ball mate. Right, it doesn't move any direction, X, Y, or Z. It just rotates in all directions. Right. So the example I have for you here, bear with me for a second, is a simple swivel and eye. So this is applied no differently than any other mate. You're just choosing two mate connectors. So here we choose a mate connector here at the center of the swivel, and then we choose a mate connector at the center of the eye, and it brings the two together. Now, this is something we cover in the basics of Onshape mates, but keep in mind, again, just remember that Onshape only solves for the active mate while you're in the mate command. So while you're in the mate, you will only see the active mate solve. If you want to see everything solve, you can click solve, and it will solve for all of the mates in the assembly. Or, of course, you can just hit the green check, which will do the same thing. But in this case, what that gives us is the realistic kind of pivoting motion that you would expect from a swivel and an eye. Right, I can grab and drag, and it's free to move in just about any direction. Right. Now, taking this one step further, the example I'd give you is the front suspension, where you have upper and lower control arms, and you have that mounted to a spindle that is free to pivot up and down, but the spindle, of course, also needs to be free to rotate. That's another example where I would use the ball mate. You'll see ball mates here that define this part to the upper and lower control arm, and you can see it's free to pivot, it's free to rotate, and you only get that with that ball mate. Now, one thing about the ball mate that makes it different is it is one of the only mates without the option for limits. Right, so if we jump into these mates, you do not have the ability to specify to determine a fixed limit to the amount of travel. But if you're looking for that rotation in all directions, no linear travel scenario, ball mate is the example I would use. The question I get asked most often is, how would you recreate swivel-like action? And the answer is ball mate. All right. So, again, if you have any additional questions, please let me know. There's a question section there. That is what I had planned to show you. I am going to stick around for just a bit, so bear with me if you would. I have one final thing that I wanted to mention, just as kind of an aside, because we've covered all of the other relations. So I did want to briefly mention it, is the linear relation. So the linear relation is really most useful if you're trying to tie linear degrees of freedom together. So let me give you a quick example of this. Take a simple example like these linear slides on a frame. And if I grab and drag one, I would expect both to move together, right? So if I grab this vertical slider and move it up and down, I would expect both to move at the same rate. And these are two independent parts mated independently. If we look at them, you can see there's a slider mate for one, a slider mate for another. They're not constrained relative to one another in any way. But if I move one, I'd expect them both to move together. And so that's an example where I'd use the linear relation. Right? So I choose linear relation, then choose my degrees of freedom. In this case, we want to choose two linear degrees of freedom that we want to tie together. Right? So if you look at our example, we have slider 3, slider 4, tie or mate the actual rails to the guides. Right? And what I want is just a simple linear relationship between those two. So I just select the two linear degrees of freedom. I hit the green check OK, and now when I move one, they both move. Oh, forgive me. I have them mated improperly here. Let's try the other. Right, so if I move these two, right, they move together. Right? So all I'm really doing here is saying this linear degree of freedom for this part and this linear degree of freedom for this part should move at the same rate. Now, what's unique about this is I could take this a step further and I could say, well, let's make a ratio. So for, every 1 inch, let's say, of movement of 1, the other should move at 2. So the other should move twice as fast. And you can see as I grab and drag it, one moves twice as fast as the other. Or if you ever have a scenario where maybe you want the directions reversed, right? Where if one moves in one direction, the other should move in the other direction. You can create an inverse relationship between the two, right? So it all depends on the scenario, the type of movement that you're trying to create. But think of any type of scenario where I have a linear degree of freedom that I want to constrain relative to another linear degree of freedom, so that when I move one, the other moves in some way. Whether they move at the same rate, in the same direction, opposite direction, different rates, that's entirely up to you. You can define all of that in the linear relation, but that's how you constrain the two linear degrees of freedom. I think the common example is going to be the two slider mates. The two slider mates give you that linear degree of freedom to move the parts, and then you're just defining, hey, here's the relationship between the two and the ratio they should move at. All right, so we've discussed all of the relations in Onshape, as well as a few of the higher level mates, we'll call them, the tangent mate and the ball mate, that we don't really get a good opportunity to discuss in kind of the Onshape basics, so to speak. So that's what I had planned for you. I am going to stick around and answer any questions that you have. So again, feel free to stick around and ask any questions that you'd like. I will make sure to stick around and to answer all of them. So, please feel free. One last thing that I would point out is if you're interested in learning more, we have a great resource available in the Onshape Learning Center, and you can find it at learn.onshape.com. The Onshape Learning Center has self-paced training, so if you want to go through and learn at your own pace, you can do that. There's instructor-led training there, technical briefings, lots of great technical content, learning content, on how to use Onshape, the most effective ways of using Onshape. So definitely a great resource if you haven't already checked it out. The Onshape Learning Center, learn.onshape.com. So as I mentioned before, please feel free to ask any questions. I am going to stick around to make sure all questions are answered. So if you have any outstanding questions, type them in. I will make sure to get to them. But that's what I had. Thank you, everyone, and have a good day.